Hello, Mr. Lee. My name is Charlie, and today I'm going to present the connection between the IRC formula and the rate of change. First, let us draw a curved arbitrary function, which is fx, shown in the red line, and let us get an arbitrary point P, on the function fx, with its x value a and its y value f at a. To begin with, because our overall goal is getting the IRC formula, an IRC value of point P, which is also the slope of tangent at point P. So geometrically, first we have to draw a tangent line at point P of the function. And we are also required to connect the idea of rate of change with IRC formula. So that means it is also necessary for us to create another additional point, which is point Q, also on function fx, with this x value a plus h and its y value f at a plus h. As for h could be both positive and negative. When h is positive, for example, h is 1.5, point Q is on the right side of point P. When h is negative, point Q is on the left side of point P. And at this time, when h is negative, point Q and point P could form the preceding interval to help get the IRC formula and the IRC value. When point Q is on the right side of point P, point Q and point P could form the following interval to help get the IRC formula and IRC interval. And at this time, when we are connecting point P and point Q, whether point Q is on the left side of point P or point Q is on the right side of point P, we could also create the secant line between point P and point Q. And as the formula slope of secant equals to theta y divided by theta x, actually for both preceding interval and follow interval, the formula is the same, because they all describe the difference between the y value of point Q and point P divided by the difference between the x value of point Q and point P. As we also recall the ARC formula, ARC equals to f at a plus h minus f at a divided by a plus h minus a. For both preceding interval and follow interval, they are also using the same formula, because they are also describing that the y value of point Q minus the y value of point P divided by x value of point Q minus x value of point P. And as we all know that ARC is exactly equal to the slope of secant between point P and point Q. So we can combine the two formulas above. And then when we make h approach 0, we could also see that point Q is approaching point P. For example, when we move the h value from 1.5 to 1, we could see that the point Q is moving towards point P. And at the same time, the slope of secant is getting closer towards the slope of tangent. And the secant line between point P and point Q is also getting closer towards the tangent line of point P. So that leads to approaching. When we describe approaching, we could describe when h is approaching 0, point Q is approaching point P, and at the same time, the secant line is approaching the tangent line. The number of secant is also approaching the number of slope of tangent. This is the same when we have the preceding interval. When Q is approaching P, H is approaching 0, secant is approaching tangent, and the number of slope of secant is also approaching the number of slope of tangent. So the distance between point Q and point P could actually be described as the absolute value of H. And that leads to the concept of limit, as we can use in this formula. When we're describing the limit concept, we're also controlling that A is approaching 0. And when A is approaching 0, we could observe the value to change, the value of f at a plus h minus f(a) divided by a plus h minus a to change. And that is the formula of the first principle. The slope of tangent equals to, when h is approaching 0, the value of f at a plus h minus f(a) divided by h. That is the development of the IRC formula and the first principle, with this connection of rate of change. Thank you, Mr. Lee.